Hello everyone, this is Ömer here from Asymptotically University. Today I'll make a presentation for IEEE Greencom 2024 entitled as the Asymptotically Optimal Scaling for Energy Harvesting Wireless Sensor Network under Stochastic Data Arrival Process. First, we'll make an introduction, then we will give a system model and the problem definition, then we will introduce our technique, uniformity and model policy Europe, then we will show the performance of Europe, and we will talk about the numerical result, and we will conclude our work and consider the future work. Okay, now we consider a problem where we have a fusion center which collects data from the surrounding nodes. Think about there are n nodes, m nodes, and the fusion center has k channels. So it schedules the m nodes and choose k out of m energy harvesting nodes in each time slot. For a chosen node to send a data packet, they need to have sufficient energy to transmit the data packet, and they should have a data packet, at least a data packet to transmit a data packet. If the buffer is empty, how we can send the packet? Okay, in that case, the fusion center can learn battery and buffer states by some additional cost, like feedback, by using some feedback, and try to learn whether the battery has sufficient energy or not, or the buffer is empty or full, or at least includes one packet, and it has some complexity for it, and maybe more. From a practical perspective, it is interesting to consider the case without feedback, because the feedback is not a reliable way. Sometimes even you cannot learn that via the communication side, or no, you cannot learn 100%. So in that case, we don't have feedback, so no knowledge about energy harvesting process or instantaneous battery state of nodes, and no knowledge about data arrival process and instantaneous buffer states of the nodes. It only knows outcomes of previous transmission tasks. For example, if a node transmit a packet, then it learns and say, okay, I don't have any I cannot send any packet just now, or I couldn't send a packet in previous time slot. Okay, there are several approaches in the literature. The dynamic programming, it has a 70 decades ago, but it is an old technique. Also reinforcement learning, but it has a complexity and convergence issues. Restless multi-term bandit is a popular celebrated operation research problem. And some people formulate the problem as a restless multi-term bandit. And the optimal solution for that problem is NP-hard. And some people propose a simpler myopic approach, and it doesn't consider the future rewards and generally suboptimal. The closest works are round-robin based myopic policies by these two, these two work, but they are generally suboptimal in especially non-uniform energy harvesting and data arrival process, because they are round-robin based techniques. And they just achieve optimality for two specific cases. Think about the general case. An optimal or asymptotic optimal solution for a general case, energy harvesting and data arrival process. Is it possible? And we have a system model, a fusion center with K channels, schedules, M energy harvesting nodes. We have the same assumptions with the previous works. No interference, no failing, but different assumption from the previous work. We have not only infinite battery, but also infinite buffer assumption, no battery leakage, M over K may be non-integer. In the round robin, it cannot. We have, from these, by using these parameters, the PIT is the policy, PIT is the remaining energy in the battery, the remaining data in the buffer, and that is the throughput. And for a node to transmit, for a node I to transmit a data packet in time slot T under policy pi, that node need to be scheduled. And it should have at least 1 unit of energy, sufficient energy to transmit one packet. And also it need to have a packet to send. If all satisfies, then it can send one packet in that time slot. Otherwise, it is zero. That shows the evolution of energy harvesting process and data arrival process. That is instantaneous energy harvest and data arrive in time slot T. There are some several definitions. Okay, we not just consider the maximization of throughput. We also consider the maximization of fairness index. Okay, we also consider fairness by considering J fairness index, a popular one. We define the user measure, user allocation in that case. That is the individual throughput. That is the possible throughput. Okay, we have several definitions. That is the intensity, the integer part of the minimum data arrived and total energy by all nodes over time horizon T. So we will show that later. Admissible energy harvesting and data arrival process. It means if the optimal policy, okay, if the optimal there exists an optimal policy whereby we can receive all the data packets can be sent by sensors, then it is an admissible process. A policy pi is called asymptotically throughput optimal. So if you know it achieves, it is ratio. Sorry, it is one, but if it is ratio achieves one, then it is asymptotically throughput optimal. It is efficiency optimal. And if a policy pi is called asymptotically fairness optimal, if lim t goes to infinity, J fairness index pi t goes to 1, then it is asymptotically fairness optimal. Okay, we have now we are introducing our policy uniform random order. Policy, it orders the nodes randomly. It keeps the order over the time horizon. It operates as below. It schedules the first k nodes according to order. So think about we have 8 nodes and the fusion center has 3 channels and it schedules the first k nodes. In this case, 3 nodes. And if a node transmits a data packet, then it continues to schedule in the next time slot. Otherwise, it continues with the next node according to random order. Could you see? In the first node, first slot, none of the nodes can send data. So fourth, fifth, and sixth continue. Here, the fourth cannot send, and then 7 continue. Then 8, then 1, 2. The cyclic order continues. And the performance of Europe. We have a very, simple but important lemma. Optimality for a node. We say that if the battery of the node is less than 1, okay, but the remaining energy in the battery of node I is less than 1, or the remaining energy is less than 1, so it means the QIT is 0 for a node I, then the throughput achieved by that node is optimal under that policy. So because nothing more you can send. So Europe, in that case, if you cannot send the packet, in that case, if you, in that case, you cannot send the data packet more. So Europe benefits, so make inference from the idle slots, say, because we cannot send any data packet. We cannot receive any data packet from that node. So we already achieved the optimal. The idle slots means that you achieved the optimal for that node. So Europe benefits makes inference about that. Okay. Europe can achieve near optimality in throughput over finite time horizon, but also asymptotically throughput optimality. And it goes to, 1, that is the ratio. That is the efficiency. And from the lemma, optimality for a node, you can see that that is 0. Okay, you cannot send any more packet. So it is, in that case, we can say that VI pi Europe T over EI T is in fact 1. So that is, okay, the ratio is close to 1 over a time horizon, finite time horizon T for general admissible and energy harvesting and data arrival process. For the fairness, the issue is similar. In that case, we use the user allocation, and in that case, that is 1 and 1 for each of them. And from this formula, if you put 1, 1, 1, 1, 1, 1, then, the fairness goes to 1. Okay, could you see? And I want to also show the numerical result. In the numerical result, we consider efficiency. Efficiency is the ratio of the throughput of policy pi over the throughput of optimal policy. Okay, the efficiencies of Europe and MIP policy. The Europe always achieves asymptotically optimality, but the MIP policy cannot achieve even the 0.8, 80% of the optimality, less than that. Could you see? That is valid for IID, independent identically distributed case processing. Now, we instead of the intensity, instead of the 20% traffic intensity, now we have a very busy traffic intensity. It is still admissible process, but very, very busy. Think about if it is less than 1, it is admissible. If it exceeds 1, so it means you cannot collect all the data the sensors can send to fusion center. Okay. If rho is greater than 1, it is inadmissible. You cannot admit all the data. But here, it is still can admit, but a bit busy schedule. Even in that case, Europe is asymptotically optimal. And Europe optimal and goes to asymptotically optimal. But it is the MIP policy even achieves less than 50%. When you consider the Markov case, it is quite similar to the IID case. And could you see, again, it is similar to IID case. So I'm continuing with the inadmissible case. It means that, in that case, it means that the sensors can send data 30%, 38% more than the fusion center can schedule. So it is inadmissible case. Even in that case, the Europe achieves maximum thing. And, it is not 1. Why? Because the 1 is not possible in that case. 1 is not possible. Even the optimal one, from definition, even the optimal one is about 0.71 something. And the MIP policy achieves even less than 0.4. Again, it is similar. And when you consider the fairness, especially even in the admissible case, admissible but high intensity traffic, the Europe achieves almost perfect asymptotically optimal fairness, but MIP policy achieves 90%. Could you see? So has some loss. And in an inadmissible case, Europe is still nice, but the MIP policy achieves less. But let me say, in infinite buffer case, in inadmissible case, Europe achieves less efficiency. Why? Because it is inadmissible. It is persistent. It behaves as persistent algorithm, so it loses the fairness. It starts to lose the fairness for inadmissible traffic. But for the admissible traffic, it is perfect. Europe is perfect fairness. And we have the conclusion. Okay, we consider the problem of scheduling, energizing, and data arrival nodes without feedback in a wireless sensor network. We propose an online policy. Europe, it is asymptotically optimal throughput. It achieves asymptotically optimal throughput and fairness for quite general energizing and data arrival process. Europe requires no feedback, has low complexity, and also asymptotically throughput and fairness optimal for M over K non-integer case, where my round-robin based MIP policies are even inapplicable. For further applications other than communication network, maybe robotic network or something. And that is our reference. And thank you very much for listening.